All right, let's go ahead and start it. Nope, not that. So, the syllabus says that our first test is Monday, the 14th. I'm feeling pretty confident that's gonna happen. Um, so we have to get through the end of chapter or section 3.2 by the end of this week. I think we're in good shape to do that. So I'm very hesitant to promise it right now, but I'd be shocked if we moved off that date. If we do, it'll just be to the 15th. But I won't move it any earlier. I might move it a day out, but I'm pretty sure we're going to hit that date. Any questions about anything we've done so far before we jump back in? All right, so we talked about matrix multiplication. So we're kind of getting into this realm where matrix operations aren't as intuitive as we'd hoped. So I gave you these 5 matrices, and I think we started last time with talking about not finding products, but just talking about what products of the possible combinations here, which ones would actually exist. So I think the only ones that involve A, we said were A, C, and D, A. What about B? What's the order of B? 1 by 3. So what would I be able to multiply it by? What's that? E? And in which direction? BE? So BE, or sorry, E is what order? 3 by 1. So we can multiply BE, and that'll make what order of a product?
1 by 1.
That'll be a 1 by 1. So that'll give you a single entry. What about the other direction? Does EB exist?
Yeah.
EB should exist as well. What order product will that be? 3 by 3. So both directions work there. Can I multiply B by either C or D? Which direction? BD works. And BD has what order?
1 by 2.
1 by 2. So I don't know. I always felt it was strange that the order of a 1 by 3 times a 3 by 2 does not involve something that has either 3 rows or 3 columns in it. But that's absolutely the case. All right. I think that's all that B can be involved with. What about C? CD, which direction? Okay, so both work. What's the order of CD? 2 by 2 and DC? 3 by 3. What about C and E? Do they work? Which way? What about EC? All right, good. So what's the order of CE?
2 by 1.
2 by 1. So yeah, we're not going to find all these, but I just wanted to kind of get a sense of recognizing when a product can actually be talked about. So any questions on making that determination? So 2-part question here. Can we figure out when the product of 2 matrices exists? And if it does, can we figure out what the dimensions of that new product is going to be? Okay. So now let's actually go ahead and do one. So 2 matrices A and B, I want to find AB. Can I even do that? What's the order of either one of these? They're both square, 2 by 2. And if I multiply them, I should get what? A 2 by 2. Did we talk much yesterday about, so we talked a lot about when this can happen. Did we talk much about how it does happen? Rows into columns. Did I go any deeper than that? Okay, so let's, at least to start this process, let's go somewhat slowly. So let's write these side by side. So we've already said that multiplying a 2x2 matrix by another 2x2 is going to yield a 2x2. So I'll give myself a lot of room for this. So what goes in this first entry? What goes in that first entry is multiplying essentially row 1 by column 1. So this matrix that we're about to build has 2 rows, 2 columns. And the way you get any entry in this matrix, so let's call this, let's say that A times B equals Y. Then these entries are going to be like Y11, Y12, Y21, Y22. So we talked about yesterday about like how to index these things. First part of that subscript is the row number. Second part of that subscript is the column number. If I want to get the value of Y11, row 1, column 1, that comes from multiplying row 1 of this left-hand matrix by column 1 of the right-hand matrix. And we basically go component by component, kind of like you would a dot product. So this first component, or this first entry, is going to be 1 times 5 plus 2 times 7. Any questions on how I built out that first entry? All right, we'll clean up all these numbers and simplify everything, but let's kind of fill out this expanded one. What's going to go in, how am I going to find Y12? Right, so yeah, that exactly. So that's going to give me 1 times 6 plus 2 times 8. What about Y21? Okay, so tell me what products I'm going to add together. 3 times 5 plus 4 times 7. And finally, what goes in our last entry, 2, 2? Okay, so 3 times 6 plus 4 times 8. So I think this is the most, of all the things about this that are probably cryptic and non-intuitive, this is probably the most cryptic. I want to stop here and make sure everybody gets their questions answered. Are we okay with how we filled out this product matrix? If we're okay with that, then we can clean it up a lot. 5 plus 14 is 19. 6 plus 16, 22. 15 plus 28, 43. And 18 plus 32, 50. I believe. Double check me, I'm doing this all in my head. Questions on how this works? Maybe like 13 or 14 more and then I'll call you experts. Here we go. All right, let's find, so let's get away from square matrices. I'm asking you to find A, B, and BA. Can I even find both of those things?
Yeah.
Okay. So AB will equal 2, 4, 6 times this column vector 3, 5, 7. And what order product will this be?
One by one.
One by one, we sure? Let's make sure. What's the order of A? It's actually not 3 by 1, it's 1 by 3. It's a single row and 3 columns. So remember, it's row by column. So then B is what order?
3 by 1.
3 by 1. So 1 by 3 times a 3 by 1. If those, so let me just write this down. Here's the product we'd like to do. 1 by 3 times 3 by 1. What's the condition we gave for the product to actually exist? Right, so these inner dimensions have to be the same number. And if those are the same, then the product is how big? Or of what order? The outside dimensions. So yeah, we're looking for basically a matrix that only has one value in it. So how do I find the value that goes in there? Go ahead.
1 by 2 and 3, and then 4 and 5 and 6 and 7.
Yep, so the way you get, so what's the only entry in here? I'll stick with this y11, right? So the way you would get y11 is to multiply row 1 by column 1. That just happens to be that just happens to be exhaustive. That's the only row and column I can deal with. So yeah, 2 times 3 plus 4 times 5 plus 6 times 7. All told is 6 plus 20 plus 42. All right, so that's AB. One thing we talked about last time is that, in real numbers, I don't care what order you multiply numbers in. The results can be the same. Matrices don't behave that way. So BA is going to look totally different. So I'm going to multiply 357 by 246. What order will that product be? That'll be 3 by 3. Go ahead. Maybe. What do you mean by that? Okay. Okay. And that's, yeah, exactly what happens here, because the way we do this, it's always you take an entire row from the left-hand matrix, multiply it by a column of the right-hand matrix, right? What do the rows look like in this matrix, though? They're just singles, right? Same with the columns here. So this 3 by 3 matrix is going to look like this. 3 times 2, 3 times 4, 3 times 6. And then 5 times 2, 5 times 4, 5 times 6, 7 times 2, 7 times 4, 7 times 6. So yeah, not at all a coincidence that we have like that pattern woven through there. How we doing? Right. What the heck does that mean? What do you think a squared means? What does it usually mean? Yeah, so in this case, yes, means the same thing. So in real numbers, that means to multiply something by itself. We're gonna do the same thing here. So if I want to solve this equation, I should probably figure out what a squared is. What kinds of matrices does squaring work with? So for example, if I go back here, could I square A or B? Either one? Yeah, 1 by 3 times a 1 by 3 doesn't work. 3 by 1 times a 3 by 1 doesn't work. What about those? Can I square those?
Yeah.
So what's the difference between those matrices and these ones here?
The middle matches.
So yeah, I can only square matrices that have the same number of rows and columns. Otherwise, the multiplication fails. Or we call these kinds of matrices square matrices. It's a 2 by 2. It's an n by n. So if I wanted to find this product, write it out this way. All right, so this is what squaring a matrix looks like. Help me fill it out. What goes in the top left?
X squared plus 3y.
X squared plus 3y. X times x plus 3 times, sorry, x times x plus 3 times y. How about the other entry in the first row? 3x plus 3y. All right. 2, 1. Xy plus y squared. And finally, 3y plus y squared. Okay, so now we have a squared. We would like to know under what conditions a squared and a are equal. We talked about matrix equality last time. So how would we get equality from this? So let me write down the equation we're essentially trying to solve. X3 yy equals this matrix that we just put together. X squared plus 3y, 3x plus 3y, xy plus y squared, 3y plus y squared. Okay. Do you have a suggestion?
Yeah, we just have.
Yep. So I can essentially write 4 equations. X equals x squared plus 3y. 3 equals 3x plus 3y. Y equals xy plus y squared. Y equals 3y plus y squared. Can I ever satisfy any of these? Go ahead. Yep. Give me an example. What's a good solution here? The middle two? Okay. I'm hesitant to divide by y because is there a chance y could be 0? I think y can be 0. I think when x, so I didn't see that possibility yet, but I'm pretty sure when x is, oh no. Yeah, when x is 1 and y is 0, I think this works. So because I'm not yet sure that y is non-zero, here's what I will do. I can factor it out because that's not really dividing. I'm just separating things. So this second or this third equation here, I'll rewrite as y minus xy minus y squared equals 0. Then I can factor out a y. Gives me y times 1 minus x minus y equals 0. So now that I have two factors multiplied together equaling 0, what's going to make this whole thing equal to 0? Really, if either part of it is equal to 0. So y equals 0 is something I can look at. 1 minus x minus y is another condition. Question so far. Let's see what happens when y equals 0. What does that tell me about x? If I plug y into this, if I plug 0 in for y in this top equation, what do I get? X equals x squared. When does that happen? It doesn't have to be 1. Well, it can be 1, but there are other possibilities. If I bring everything over and do the same kind of factoring thing, I get x times 1 minus x equals 0. No, 0 and 1. Because if x equals 0 or 1 minus x equals 0. So now here's what we have. We found that y equals 0. And as a consequence from y equaling 0, we got that x could equal 0 or 1. So here are some possible solutions: 0, 0, and 1, 0. But we have 4 equations we have to satisfy, right? We have to make sure that everything is satisfied by both of those. Does 0, 0 work in all 4 of those equations? No, it fails the second one, right? 3 does not equal 3 times 0 plus 3 times 0. So even though that 0, 0 satisfies some things, not everything. How about 1, 0? I think so. So, yep. So this one's fine. Is that the only solution, though? So the other piece of information we got from this equation here is that basically x plus y equals 1. Can we do anything else with that? 0, 1 definitely fits that. Go ahead. Okay, so let's do that. Let's bring some things together. So if I combine the linear y's, I get 0 equals 2y plus y squared, which gives me that 0 equals y times 2 plus y. So what did I find out here? Y equals 0, y equals negative 2. So there's something we haven't explored yet. If y equals negative 2, then what would x have to be? 3? How do we get that? Maybe that comes from this x plus y equals 1, right? So now let's make sure of this. We think we have a possible solution at 3, negative 2. But now we have to make sure that it fits all 4 of the equations that we've been looking at. What do we think? I think that top equation is fine. I think the second equation is also good. Uh-huh. No, because I combined. So the first thing I did here, which I didn't write down, is basically I subtracted both sides by y. That's why it's a 0 equals 2y. I feel like this is okay. I think it fits all four of our equations. Is there any possibility there could be others? I don't think there could be because so the two equations we so we got like concrete x values from this top equation, right? Or where did this come from? Yeah, where did we get x equals x squared? Oh, so we got y equals 0 first. Okay, so the first thing we dealt with was this third equation, which gave us these two conditions. And then from y equals 0, we got that x equals 0 or -1. The origin we eliminated because it doesn't fit everywhere. Yeah, I think this is an exhaustive search. I think we found everything. Questions? All right, let's go ahead and keep on moving. So, is this something we can do? So I want to find another matrix B that where if I multiply it by A, I'll just get A back. So first things first, what order does B have to be for this to even make sense? 2 by 2? You have a question? Oh, sorry. Okay. So if A is a 2 by 2, and I want the product to be 2 by 2, I have to multiply this by another 2 by 2. So here's basically what I'm trying to do. I'm going to multiply this by something, and what I want to come out is A, B, C, D again. How would I figure out what goes inside this? Go ahead. 1, 0, 0, 1. How do you know that? Right. So what's the first row times the first column? A times 1 plus, sorry, A times 1 plus B times 0. That's just A. First row times second column, A times 0 plus B times 1. That's just B. And that'll shake out the same way with the second row. C times 1 plus D times 0 is C. So yeah, this matrix right here will, and I could multiply it on either side. So right here, I'm multiplying that matrix on the right, but you could also make the multiplication from the left, and it would still give you A. So this special matrix that we just wrote down, is this something you've seen before? So this thing right here is called the identity. So you probably haven't thought about it in a while, or maybe you've never thought about it, but in real numbers, there's always an identity. So if I give you a real number, there's something I could multiply it by that always gives you K. What is that?
1.
1. So 1 is the identity in regular multiplication. We can't talk, there's no like, you can't talk about just 1 in matrices, but we have this matrix that does the same kind of function. If I multiply it by a matrix, it doesn't have any effect. It just passes the same matrix back. So that's called the identity. So the way the identity matrix is always structured is it's always square. It has to be same number of rows and columns. It only has two values in it, 1 or 0. 1 if the column number and the row number are the same, 0 otherwise. So I just showed you this matrix, I2. I3 looks like this. So basically along that major diagonal from top left to bottom right, that's populated with 1s. Everything else is 0s. So if you multiply your matrix by the appropriately ordered identity matrix, you'll just get the same thing back. How are we doing so far? Okay. All right, so let's do some things with inverses. Okay, so let's go back to real number land for a second. If I gave you this equation right here, ax equals b, and I wanted you to solve for x, what would you do? Divide both sides by a, right? And then I get x equals b a. No, what am I talking about? That's what I said. X equals b over a, right? So divide by a number and you can isolate x. Now, what if a and b are matrices and x is a column vector that's the right size to make a and b happy? How would I solve for x in this case? Go ahead. X equals b times the inverse of a. I almost agree. I'm very close to agreeing. So let's talk about this first. What's special about this inverse matrix? I have not talked about the inverse matrix yet. Is this something that is brand new to most of us? Okay. Let's go back to real numbers for a second. An inverse, like in like generic abstract algebra, an inverse is a number like in multiplication. If I have a real number k and I multiply it by an inverse, then the answer will be the identity. What's the identity in real numbers? 1. What's the thing that I can multiply by k to get 1? 1 over k. 1 over k is you probably have never thought about it this way, but like most real numbers have a multiplicative inverse. We call it a reciprocal. There's only one number that does not have a reciprocal. What is it? 0. Can't multiply 0 by anything to get 1. So matrices also have inverses. There needs to be something that I multiply a matrix by to get 1, or the matrix like analog to 1. So that is the thing called an inverse. If I multiply a matrix by its inverse in either direction, I'll get the identity matrix. So that's what's special about this matrix called the inverse. Now, I said that I almost agreed with this. One thing to be careful about with multiplying with matrices is that it's really not enough to say multiply both sides by something, because the direction of multiplication matters. So in this case, this looks like I multiplied A inverse on the right, right? Which means what I would really have is this: AX A inverse equals B A inverse, which it really looks like the A and the A inverse are going to cancel here, but because that multiplication of X is in between them, they don't cancel. So what's one little modification I can make to that multiplication? Like, how would I really isolate X now that we've talked about this new thing called an inverse? Okay. If you multiply it on the left, here's what happens. You get A inverse A times X equals A inverse B. A inverse times A is IX equals A inverse B. What's the identity times X? Just X. So X equals A inverse B. So that's a little bit of a primer on this special matrix. If a matrix has an inverse, we call it basically that raised to the power of -1. That's the notation. Same as it would be for like inverse function or inverse sine. Same kind of thing. Questions so far? So I don't know if it's good news or bad news. There's no such thing as matrix division. We'll talk about just multiplication by a specific thing that acts like division. So how do we find these things? So the only kinds of matrices that can have inverses are square. Not all square matrices have inverses, but all matrices that can be inverted are square. So if it exists A inverse or A to the negative first, that's the inverse matrix. And this is, by definition, what makes the inverse the inverse. If I make that product, what I get back is that matrix that has ones along the diagonal, the major diagonal, and zeros elsewhere. So the game here is like, I want to give you a matrix and be able to find the inverse, but I want to make sure we understand like kind of what is the point of this thing. So are we okay with the rationale? Like, what is the inverse matrix? What is its purpose? So let's find the inverse for the smallest matrix we can. So 2 by 2. So I want to come up with a formula for the inverse here. So I want to solve for this W, X, Y, and Z. So basically what I'm saying is this: A is equal to A, B, C, D. And when I multiply from the left by this W, X, Y, Z matrix, I get 1, 0, 0, 1. And by setting that product equal to the identity, I should be able to invert any 2 by 2 matrix. So what's this product here going to be on the left if I multiply these two matrices together? AW, yeah. That's not exactly what you said, but I have reasons, I promise. How about the next entry over on the right? Not quite. So when we multiply, what do we take from this matrix here? Take a row, and we take a column from here, right? So the top right entry of our product, that's going to be which row? So if I want to fill in this blank here, what row is this? Row 1, what column is that? Column 2. So to get that, I will multiply row 1 by column 2. So what's that going to give me? Is that what you said? Excellent. I'm sorry. I was moving on to the next row. All right, so second row, column 1. I promise I have a method for the reason that I'm not quite writing down what you're actually saying to me. You are right, though. And then finally, by plus dz. And I want this to be true. I'm setting this all equal to 1, 0, 0, 1. So how can I make these matrices equal? Or what would actually make them equal? Yep. So all four corresponding pairs of entries need to match up. So AW plus CX equals 1. BW plus DX equals 0. AY plus CZ equals 0. And BY plus DZ equals 1. And just a reminder here, the thing I'm looking for is a solution for WXYZ. In terms like A, B, C, and D are like unknown constants. But I want to isolate W, X, Y, and Z in terms of those constants. So how can I start doing that? Got 4 equations, 4 unknowns, which is kind of a weird place to be. Go ahead. Which ones? Of the ones that are equal to 0? You could. I think that would give you. Let's try it. So if we put these together, what do we get? Here's my concern with that. You basically condense these 2 equations into one. And now I have 3 equations for my 4 unknowns. So I'm going to suggest something slightly related. I'm still going to take advantage of the fact that both of these are equal to 0, but I'm going to do it one at a time. I know that BW is equal to negative dx. And I know that AY is equal to negative CZ. So the first thing you said was basically like, I think your point was that elimination is not going to happen. Like there's nothing we can't like add or subtract these equations and get rid of any terms. So I think we can do some substitution now. Should we solve for W or X here? Sure. W equals negative D over BX. You want to solve for Y or Z? Y sounds good. Y equals negative C over A, Z. If I do some substitution, what does that buy me? I get A times negative D over B times X plus CX equals 1. What variables are in that equation? I know there are a bunch of letters, but which ones are the actual variables I'm trying to solve for? There's only one variable in that equation. It's only X, so that's actually really convenient for me. Let's go ahead and solve it for X. So minus AD over B times X plus CX equals 1. If I factor in X, I get what? C minus AD over B equals 1. So X is going to be equal to what? I'm gonna find the common denominator here. So CB minus AB all over B. So then 1 over that would just be the reciprocal, right? B over CB minus AB. What's that? Oh yeah, we'll drop that off, didn't I? Factor on X, it should be is that the mistake I made? So X equal to B over CB minus AD. Okay. Okay, so I'm running out of room very quickly to find this inverse. So let's kind of I believe strongly we could find, so we solve for X, right? From there, I think we could plug it back into here and solve for W. And since we wrote these, I think we could solve for Y and Z. So I think we can get formulas for all those, but I'm not going to try to squeeze that into the space we have. Here's basically what the inverse of that matrix is going to look like. So if A is a 2x2 matrix, a generic 2x2 matrix, every square matrix has a thing called a determinant. And basically what that comes from is this. Taking this product along the major diagonal, so A times D, minus this product B times C. Your matrix has an inverse if that determinant is anything but 0. And hopefully that'll be clear when I show you what the inverse is. Here's the inverse. So I'll rewrite this another way. 1 over not AB, AD minus BC times this matrix that's related to A but kind of shuffled around. So basically A and D got their positions changed. B and C are in the same position, but they are now negated. Go ahead. Yeah, so the only kinds of matrices that have inverses are square. I'll give you an example. There's some inverses, some square matrices like 1, 1, 2, 2. This does not have an inverse because if you were to do the determinant on this, it would be what? 0, 2, 1 times 2 minus 1 times 2. So some square matrices cannot be inverted, but the only kinds of matrices that have inverses are all square. How are we doing so far? So for a 2x2 matrix, this is a good way to get the inverse, as long as your determinant is not 0. How are we doing? So if I throw one at you, can we find A inverse? How do I find the inverse of a 2x2? Probably the last thing you wrote down. Go ahead. Right. So the determinant will tell us if we can even finish this. The determinant in this case is what? Okay, so 4 minus 6, -2. We're good. We have an inverse. So our inverse is going to be 1 over the determinant of A times this like a modified version of A. How do we modify A to finish this up?
Switch. What we would make D, which is
Yep. So I'll start with the one and the 4. They change places, and the 2 and the 3 they change signs. So then our inverse is basically, I'm going to multiply everything inside that matrix by the scalar -1/2. So -2, 1, 3/2, -1/2. Questions on how we got that? How can we make sure we're right? If I multiply it by A, what should we expect to happen? We should get the identity. So let's make sure that happens. So multiply by 1, 2, 3, 4. Row 1 times column 1 gives me what? -2 plus 3. Good so far. Then -2 times 2 plus 1 times 4, 0. 3/2 times 1 minus 1/2 times 3, that's 0. And then 3/2 times 2, that's 3, minus 1/2 times 4. So 3 minus 2 is 1. So yes, that inverse is confirmed. So if it's truly the inverse, the multiplication works from either direction. We're not going to go through that, but it would also work from that direction. Questions? How about this one? What's the inverse of this matrix? There's no determinant. So the determinant of A is what? 0. So what does that mean? No inverse exists for this matrix. So we're done. So that determinant is, it tells you a lot of things. Like the biggest thing we're going to be interested in right now is that it'll tell you if your inverse actually exists. So we've solved equations a bunch of ways. Let's use an inverse now. So I have a system of 2 equations, 2 unknowns. How would I rewrite this as a matrix system?
if the regular figure,
Yeah.
that'd be a 3 by or a 2 by 3.
That's if you want to do like an augmented matrix, right? So but when we write an augmented matrix, we're kind of like condensing together 3 different matrices when we do that. What that really comes from is basically this multiplication. I have a vector A, or sorry, a matrix A, which is 2 by 2, a vector X, which is basically contains the things I'm trying to solve for, which is 2 by 1. And if I multiply those together, I should get another 2 by 1, right? So what's contained in each one of these things? So A is going to be my coefficients of X and Y. So 1, 3, 2, -1. And then what lives in that vector X are the unknowns I'm trying to solve for. So X, Y. And then what happens if I multiply a row by a column here? I get 1x plus 3 times y. What does x plus 3y equal? According to this system, 8. And then 2x minus y is equal to 9. So when we write down that augmented matrix thing, what we're really doing is kind of condensing the matrices A and B into one thing, knowing that the vector x always looks the same. So basically, it's a little bit of a shortcut. So the reason I bring all that up is now that I've kind of written it as this 3 different matrices in this equation, what's the thing I'm trying to solve for? X and y. So I would love to be able to isolate this. How would I isolate that?
The inverse of that one.
The inverse of A, right? So yeah, let's give these names: A, X, and B. I would like to multiply both sides by the inverse, but remember, it matters how I multiply. So where do I want to multiply the inverse? On the left of both sides of the equation or on the right of both sides of the equation?
Well,
On the left, because that way it'll actually cancel A. So here's basically what I'm doing in my equation. Here's the thing I gave you. Even though I didn't give it to you as a matrix, we rewrote it like this: AX equals B. Then we're going to multiply both sides by whatever the inverse of A is. The left-hand side becomes what? Just X. X equals A inverse B. So we don't have A inverse, but if we get A inverse and then multiply it by B, we should get our solution. So before we actually do that, any questions about why that is going to work? Are we okay with the idea that this is a valid way to go after this solution? All right. If we're okay with that, then how do we find A inverse? Need the determinant. What's the determinant going to be here? Okay, so -1/7 times something. What's this other matrix going to look like? -1, -3, -2, +1. So again, the top left to bottom right diagonal, swap those entries. And then the minor diagonal, the 3 and the 2, change their signs, but keep them where they are. So one other, I think all of us, myself included, are all kind of fraction averse. One way we can keep this is like this: -1/7 times -1, -3, -2, 1. So now when I do this product, A inverse B, would you rather multiply by a fraction once or more than once? Once. Or at worst, twice. Basically, if you can keep this as a scalar multiple that you can handle at the very end, you don't have to, but it's definitely something you can do to maybe streamline things. So now this thing right here is A inverse. This column vector is B. And when I multiply these together, I should get X. I should know what X and Y are. So I'm going to keep this scalar till the very end. What do I get when I multiply A by B? -8 minus 27, so minus 35. And then -16 plus 9, -7. Or 5, 1. Does that actually make sense with our system? If we plug in 5 for X and 1 for Y, that should work, right? So yeah, yet another tool you can use to solve a system of 2 linear equations. Any questions so far? All right, let's. Ooh, big matrices. How do I find the inverse of this thing? Go ahead.
Well, when you
Right. So that's a good thing to always focus on, is that I don't care how big the matrix is, the inverse always has the same purpose. Like, so when I've written this thing down a few times, A times A inverse equals I. You know, this thing is not like beholden to any order of matrix. So for a 2x2 matrix, I was able to give you like a nice canned formula. There is a nice canned formula for a 3x3 matrix. If I showed it to you, you would not ever want to see it again. It's very long. But it exists. You would never remember it. It would be a waste of your time to try. But we can still invert things like this. And that's because we know what the objective of an inverse is. It's another, so how big is the matrix be? How big would the inverse have to be? What would the order have to be? 3x3, because I want to multiply a 3x3 by something to get the 3x3 identity. This A inverse has to be 3x3. So basically the game is this. 3 times 6 times -3 times -2 times -4 times 4. I don't know why I said times so many times. It's not really what I'm doing. Times A inverse equals the appropriately sized identity matrix. So you all saw how much room I was using to solve a 4 variable system to get that formula. Getting 9 variables would not be worth our time or the space or the headaches. So what are we going to do here? I thought I had another slide here. Nope. Okay, so here's basically how the process works. We are not going to finish this today, but let's at least get started so we have a jumping off point for tomorrow. I'm ominously moving this up here because I know how much room it takes. So we're going to set up a new kind of augmented matrix. It's going to look like this. It's going to be in 2 halves. And typically when the augmented matrices you've set up on this right-hand side of this line, you have a single column, right? And that like usually holds your whatever constants are sitting on the right-hand side of the equal sign. For this, what's going to be on the right-hand side of this is another 3x3 matrix that looks like this. And the reason we do that is this. Basically, what's going on here is what an augmented matrix is like a shorthand for is I'm multiplying this matrix by some mysterious vector or matrix in the middle, and it equals whatever's on the right-hand side of this equal sign, right? Usually what that has looked like for you is this. I'm multiplying my 2 by 2 like coordinate or coefficient matrix by xy, which is the variable matrix. And what that equals is whatever constants are on the right-hand side. Now what I'm multiplying is a matrix, a 3 by 3 matrix by a 3 by 3 matrix, and that equals the identity. So the goal here is basically this. I want to know what I can multiply A by to make the identity happen. So my goal is this. On the right-hand side of this, I'm going to have A inverse. Because on the left-hand side of this, I will have the identity. What's the process called where I make A look like this 100010? That's the reduced row echelon Gauss-Jordan lineage. So something we've done, now we're using it for a completely new purpose. So the process is not really any different, but we do have the extra complication of now I have to keep track of all the consequences on the right-hand side of that vertical line. So let's get started. Maybe just a couple of steps. Do you have a question? Or do you have a suggestion?
Yeah.
Go for it. You add row. What will that do? Okay. So we'll get a pivot. So row 1 plus row 2, put that to row 1. All right, so I'm going to write the second 2 rows because I'm not doing anything with them, or I'm not altering them. All right, what's this top row become? 1, 1, 2, negative 1. Yeah, 1, 2, 1. And 1, 1, 0. Okay, any questions about why we did that? So we got a pivot in column 1. Now that we have that pivot in column 1, what's a good thing to do next? Get zeros in the rest of the column. So give me 2 operations that are going to do that. Go ahead. Two times row 2 to row 3. Okay. So what are the top 2 rows going to look like? Whatever they look like now. And I got to be more careful going forward. All right, what does row 3 look like? The whole point was to put a 0 right there. And then negative 3. 2 times 4 is 8. Minus 13 is negative 5. That should still be a 0. That should be a 2. That should be a 1. Okay, I got 210. I'm going to stop there, but please double check me. it's just, it's one of those things, like I said, like it's simultaneously easy to make the operations, it's also easy to mess them up. And then it's very hard to find the mistakes once you've made them. Do I have your blessing on what's up here so far? Okay, now you're responsible for it. All right, I'll see y'all tomorrow.